Hello, and welcome back to CS500 Design and Analysis of Algorithms. We are in chapter 4 talking about amortized analysis, which is a way of getting more realistic predictions about the performance of algorithms as opposed to the worst case setting. And uh, a subtle point about the concept of amortized analysis is that we here analyze data structures as opposed to single algorithms, and more precisely, data structures that are provide operations that are executed repeatedly. So we talked about repeatedly incrementing when we analyze the binary counter in the amortized setting, and we talked about repeatedly calling extract min and repeatedly calling decrease key when we analyze the amortized cost of Fibonacci heaps as a way of realizing a priority queue data type. So not one single call to extract bin or one single call to decrease key, but repeatedly. Also not the average case, but the worst case sequence of these operations. And one important motivation for this type of analysis is that many algorithms build on top of such data types. For example, we analyzed Prim's algorithm for minimum spending tree calculation, which would repeatedly call, do exactly that, repeatedly call extract bin, and more frequently, that's the whole point, more frequently call decrease key, and therefore the Fibonacci heap was specifically designed such that the decrease key operation has lower amortized cost, I mean constant amortized cost, than the extract bin operation. So that was our Fibonacci heap amortized analysis. And then we started talking about Kruskal's algorithm for minimum spending tree calculation, which also repeatedly calls data type, builds on the data type, but not a priority queue, but a data type for disjoint sets. And before that, we had some look at fast growing and slowly growing functions, which are becoming relevant right now, when we analyze different ways of realizing a disjoint set data structure. This is where we resume the lecture, where I am going to start the slides. So here you see the slides, and let me pull up the background and remind you of which operations a disjoint set data structure supports. And so in disjoint set data structure, we have three operations. One is a make set operation that creates a singleton set. Make set of X creates a singleton set with whose node contains a single element X, and it returns a handle, a pointer if you like, to that singleton set. Then we have the union operation. Union operation receives two elements, and these two elements are considered as representatives of the sets that they lie in. So X lies in some set that has previously been created. Y relies in some other set, that's important, that has previously been created, and the union operation is supposed to take these two sets and to combine them into one larger set and return the handle to that larger set. So let's visualize that. First, make set X creates a singleton set, that's a blue circle, containing the one element X, that's a black dot. And the user can call make set another time, creating another singleton set, and so on, many singleton sets. And next, the user may call union in order to make the data structure combine two of these singleton sets into one larger set, and the previous singleton sets are then kind of lost. They are replaced by this one larger set. So that's an important observation, that one call to union decreases the number of sets, and all the sets are always disjoint. You see that they're disjoint, right? Singletons. And when we call union, then, for example, these two singleton sets are combined into one larger set, and the previous two singleton sets are discarded. They are no part of the larger set, and therefore the resulting collection of set is still disjoint. So these are not sets anymore, only this larger set, and that is still disjoint from the remaining set. And then we maybe create another singleton set and make another call to union to combine these two into one larger set, and all the time the collection of sets are pairwise disjoint, and maybe create another pair of sets, combine them using the union operation, then making another call to the union operation, maybe with this argument, and with this argument as representatives of these two sets. So x and y here are representatives, and important to emphasize, not necessarily unique representatives. One could also call union with this and this argument. The result has always to be the same, namely combine these two sets. Let me say that again. Arguments x and y are only possible representatives of the set. So x could be this, or x could be this, y could be this, or y could be this. The result will always be the same. They combine these two sets into one. And I'm already heading at a important part, namely how can we have unique representatives of set instead of arbitrary representatives? Well, the union operation takes as argument arbitrary representatives, but at some point we will want to compare two sets and we see whether they are the same. So that's one way of doing that is by having unique representatives. I'll say more about that in a minute, but let's now continue with our example execution, repeated, making calls to union and make set. That's exactly the setting of amortized analysis. So we take the union of these two, and then we take the union of the larger set, and so on. So repeated taking unions, maybe not taking the union of these. So this is a sequence of operation where amortized analysis shows its strength. And as we're going to recall, Kruskal's algorithm exactly builds on such a disjoint set data structure by making repeated calls to make set to union, and the third operation is already announced, the find set operation. Find set receives as argument an element and is supposed to return a unique handle to the set that currently contains that element, right? So since our sets are always disjoint, that means every x lies in a unique of these sets, and we want to be able to compare these sets. More specifically, Kruskal wants to be able to compare whether two elements x and y belong to the same set or to different sets. And find set operation provides exactly that. It returns a unique handle to the set. So when we call find set with x and then call find set with y, and if x and y belong to the same set, then find set should return the same handle. That handle could be, in practice, this is going to be a pointer, but generally speaking, it should be just some unique identifier that allows us to compare. So 2 points in the same set should result in the same handle to be returned, which can then be compared with equality, whereas two elements x and y that belong to different sets should result in different handles being returned, so that we can then verify that using test for inequality. There's no order on the handles, only equality or inequality. So that's a semantics of the disjoint set data structure that we want to support. And so here you see an example. Here I have kind of taken the approach of marking or designating special elements in the set as unique representatives, the light ones. So that means whenever the user calls find set with this argument x, the return would be this element. When the user calls find set with this argument, then the return value would be this. And if the user calls find set with this argument, then of course the return value will be the same. Whereas when the user calls find set with this argument, then this is going to be the return value in this example. And we're interested in realizing the semantics in devising data structure and algorithms and analyze these data structure and algorithms in the amortized setting, not in the worst case setting, but in the amortized setting, because this is exactly what Kruskal's minimum spanning tree algorithm builds on. Remember, this is Kruskal's algorithm. So first, Kruskal creates singleton sets for every vertex in the input graph, and then processes the edges in this graph in increasing weight, right? So we have a weighted graph. We've already sorted the edges, so this is simply walking through the edges in order of increasing weight, and then checking whether two nodes belong to the same subset in this disjoint set data structure. Initially, they are all singletons, it does belong to different subsets. If they do not belong to the same subset, if they belong to the same subset, then Kruskal will discard that edge because it would create a loop and thus violate the is redundant. We're only interested in trees which do not contain loops. Whereas if they do belong to different subsets, then we kind of combine the two subsets, we combine the two trees that these subsets correspond to in the forest of Kruskal, joining them with this new edge, and then indicating that these two trees, these two subsets, have now been merged into one larger tree, into one larger subset. So this is where Kruskal calls the disjoint set union operation, and here Kruskal calls the find set operation to check whether U and V belong to same or to different subsets. If the unique handle returned is different, then according to the semantics, they belong to different sets. So this is a kind of the core of Kruskal's algorithm, the innermost loop, and this is our motivation for amortized analysis, because Kruskal does that repeatedly. It recalls these two operations for every single edge. So that could be kind of M operation called to find set, and at most M operations called to union. And so that's why we're not interested in the worst case cost of find set and union, but in the amortized set, because they execute it repeatedly. And when one execution is expensive, but the majority of them is cheap, then that's more important than having a small worst case cost. Now let's talk about how to realize this disjoint set data structure. Of course, we're going to realize that using pointers, and then if realization is to have take the root of a let's say a tree as a unique representative, and to store in that tree all the nodes that belong to that set. Now that doesn't need to be a binary tree, it could be an arbitrary tree. And our first approach in realizing this data structure is to have each set as a tree of depth 1, where the unique handle is the root, and all the other nodes are attached to the root, so the tree will have depth 1. Another tree for the other set, another tree for this set. So this is a forest, and it will have depth 1. Depth 1 is good because then we can execute find set in constant time. Namely, when the user gives us an argument x, we this is either going to be a leaf of that forest, or it's going to be a root right away. If it's a leaf, then we follow the pointer back to the root, one pointer constant time, and thus we can find the root, the unique handle, in constant time. So this is what you see here. All these pointers from the leaves to the single root of this set, the root of this set, and thus we can realize find set in constant time simply by following this single pointer. That's a constant time operation. But the difficulty or the disadvantage of this first approach is that the union operation becomes pretty costly. Maybe in the union operation, let's say the user wants us to calculate the union of this set and this singleton set. Well, now we have to kind of break ties. Which one is going to be the new unique handle of the union? Is it going to be this one or this one? And well, in the union, maybe we choose this as the new handle. Then we need to update all these pointers, which seems like a stupid idea. Seems more efficient since we already have many pointers here, simply to redirect this one pointer also to match here. But this is kind of this is a natural heuristic, but it doesn't seem to give a good worst case estimate. I mean, in the worst case, we're supposed to create the union of two sets of equal size, and then it doesn't really matter how we break ties. If the two sets have equal size, then we need to update the pointers in one set, which are as many as in the other set. So either way, it's going to be linear cost for calculating the union in this realization as forest of depth 1. So that means if we do that repeatedly n times, then that could result in total cost n squared. Linear cost for one union operation, and if we have sufficiently many sets of disposition, then we can do that again and again and arrive at quadratic running time, and amortizing means divide that by n. So we're back to linear amortized cost, which is of course far slower than we expect. Want at least logarithmic. Actually, we're ambitious. We want sublogarithmic running time. So, but at least that's a starting point. We have our first data structure, our first algorithm. We have analyzed it, and following the paradigm, now we start over again, trying to devise a better data structure and a better algorithm and analyze that again. And the next algorithm we're going to consider is the union by weight heuristic. So what does that mean? It means what I briefly said as a heuristic, and it is a heuristic here, namely when we are supposed to create the union of two sets, then we attach the smaller set to the larger set. We attach the smaller tree to the larger tree in this forest of depth 1, which is, as I said, a natural heuristic, but it seems it's only heuristic because when both trees have the same size, then it doesn't matter how we break ties. Overall, both we have to update all the pointers, but that's a worst case analysis, a valid worst case analysis. But now we want to analyze this algorithm not in the worst case, but in the amortized setting. And there it turns out that this is a rare case. The worst case happens, but it is rare. And in the amortized setting, we're going to show that the cost is only logarithmic. So that's our first improvement to the previous case. Namely, we're going to see that the union by weight heuristic of attaching the smaller to the larger tree in order to realize the union among disjoint sets in a forest of depth 1 has only logarithmic worst case cost, amortized cost. More precisely, we're going to show that whenever we have a sequence of calls to make set, to find set, and to union, n calls to make set and m calls to find set union, then the total cost is m, the number of calls to find set and union, plus n log n, the number of time calls to make set. So that means, notice that the number of calls to make set is at least as large as the number of calls to union, right? So every call to make set increases the number of sets. Any call to union decreases the number of sets we have, right? And find set does not change the number of sets. So that means the general setting, the number of calls to make set is equal or larger than the number of calls to union. So n is larger. And so then this kind of dominates, and we divide by n to obtain the amortized cost. And now we proceed to proving this theorem, right? So it's a mathematical theorem about computer science analysis, namely turning this heuristic into an algorithm by equipping it with a rigorous amortized analysis. So what we want to show is this bound on the total cost of a sequence of calls to make set, n calls to make set, and m calls to find set and to union. And we show that the total cost of m plus n log n. And then it follows that the amortized cost is logarithmic by dividing. So that's our goal here. And so let's look at an example. And so the calls to find set, we already know, take constant cost. So that's already taken care of. The thing and make set also takes constant cost. So the interesting thing is the amortized analysis of the union operation. And our, right, so make set and find set all take constant cost. Now, what is the amortized cost of union, or put differently, what is the total cost of a sequence call to union? And as I said, the worst case is when we break ties equally. So when the user wants us to merge two sets of equal size, because according to our heuristic, union by weight heuristic, we always adapt and make the smaller set now redirect the pointers from the smaller set to the handle of the larger set. So that means, when does a pointer from a certain element get updated at all? Well, if the element belongs to the larger set, then it does not get updated at all. It gets updated and thus incurs cost only when this element belongs to the smaller of the two sets, or when we have to break ties if both sets have the equal size. And when that happens, so when we have another set here, and this link gets updated, then that means the other set must be at least as large as the set that x belongs to. So when x belongs to the set of size 4, then the pointer being updated and thus incurring computational cost can happen only when there's another set already of size 4 happening, right? Or larger. Okay. So, and now the thing is, of course, these pointers will also be updated, but in our analysis, we take this different perspective and instead analyze not how many pointers get updated, but how often one pointer gets updated, one fixed pointer. And then we repeat that analysis for the next pointer. How often does the pointer from that element, from that leaf, get updated during a sequence of call to union? How often does the pointer from that set element get updated? And thus we arrive at the same mathematical result, but the analysis is tractable, as opposed to when analyzing how often these pointers together get analyzed. So that's how we analyze it, and the observation is this fixed pointer gets updated only when the union operation is called with another set of equal size or larger size. And after this call to union, then this element, and actually this entire set of size 4s, has been merged to this set, and thus has kind of become a larger set of size 8. And now we repeat the same perspective again, supposing that all these points, these elements have become part of this larger set and now forms a set of size 8. When is this pointer getting updated the next time, second time? Well, it's get updated a second time only when union is called with this set and another set of at least the same size. When union is called with this set, any element in this set, together with a smaller set, then this point is not affected, only the pointers of the smaller set get affected. So for this pointer to get affected, there must be another size to get affected the second time, then must be another set of size 8. And when does it get affected? The third time? Well, then there must be another set of size 16, and so on. Each time this pointer gets updated, that means there must be a larger set already present, and the size of the sets that must be present grows exponentially. So node's link gets updated only when its set is combined with another set of larger or equal size, and it getting updated repeatedly means there must exist larger and larger sets. And for such large access to exist, that means that the user must previously have made calls to make set frequently, so that we even already have a sufficient number of elements to form these large sets. And we say that again, for the link here from X to be updated, let's say K times. If this link get updated K times, then that means the first time there must be another set of twice the size. Next time there must be a set of 4 times the size. Then there must be a set of 8 times the size. And for this link to be updated K times, then there must exist at least one set of size 2 to the K. And for a set of size 2 to the K to exist, that means there must exist 2 to the K elements. And therefore, the user must previously have made calls to make set at least 2 to the K times. And that's really the core of the amortized analysis of this union by weight. Namely, we can now kind of charge or see that for a union operation to be expensive, or a sequence of union operations to be expensive, namely in the sense that there are K update operations incurring cost K, then that can only happen after having made 2 to the K calls to make set, and according to our amortized analysis, or if you like, according to the bank account metaphor, we can use these calls to make set in or 2 to the K calls to make set to build up a financial buffer of size 2 to the K, charging $1 extra for each call to make set on top of the constant cost. Make it be constant cost plus 1, and this extra dollar goes into a bank account. So whenever union operation or sequence of union operations is expensive, that can only happen after our bank account has already accumulated considerable financial buffer that we can now take out of, and in put differently, solve this for K. The total cost of a sequence of union operations will be at most the logarithm of n, and that's exactly what I wrote here. Sequence of calls to union, one pointer being updated, and now we repeat that analysis not just for the link from the node X, but also to the link from this node. And the links to this node, every single link can be updated at most log n times, and we have a total of at most n nodes. So the total cost of such a sequence of union operations can be at most n times log n for each. So that's our analysis of a sequence of calls to union operation based on knowing how many calls to make set the user has made and how many the user must have made for the sequence of union calls the union to be expensive. So that concludes our analysis of the union by weight heuristic, making it an algorithm with logarithmic amortized cost. Okay, that was our second algorithm and its analysis for realizing a disjoint set data structure as a forest of depth 1, this time with a union by weight heuristic, redirecting the pointers from the smaller set to the larger set. And interesting cases in the analysis when both sets have same size, and that we analyzed that and showed that this has logarithmic amortized cost. And now we want to further decrease that. So now we start over again, devising our third data structure and analyzing our third algorithm for disjoint set data structure. And all this time, we depart from the representation from the data structure of a forest of constant depth, and instead move to forests of larger depth. But of course, we want the depth to be small because, as usual, the depth is what determines the cost, at least in the worst case. And so what we now do is we're going to learn about the lazy union by rank heuristic with path compression. So that's our third algorithm, and it's so famous that it has this admittedly technical name, lazy union by rank with path compression. So what is that about? Again, we represent, we store or disjoint sets as a forest, but now the forest does not need to have depth 1, but it can have larger depth. So here you see a kind of a snapshot. Here we have kind of 5 disjoint sets, 1, 2, 3 singleton, 4, 5 disjoint sets, and these are the elements in these sets. And again, the roots are the unique handles for the fine set operation. And now the fine set operation does not have constant cost anymore, because if the tree under consideration is deep, for example here, then the fine set operation must walk all the way up to the root in order to arrive and to be able to return the unique handle. So this fine set operation is now crucially depends on the depth of the trees in this forest. So on one hand, we want this forest to be shallow. On the other hand, we saw that updating pointers in order to maintain constant depth is expensive and makes the union operation expensive. So here, this is kind of the trade-off that we're facing. The previous one had constant, previous algorithm had constant cost for the fine set operation, but logarithmic cost for the union operation. And now what we're trying to do is we're kind of trying to balance that. We reduce the cost, at least the amortized cost of the union operation, at the expense of possibly slightly increasing the cost, the amortized cost of the fine set operation, right? So let me say that again. Previously, we had an imbalance in the second algorithm, the forest of constant depth. The fine set operation had constant cost. The union operation had logarithmic cost. But our goal is to have both roughly the same amortized cost, because in Kruskal's algorithm, they're both called roughly the same number of times. So it doesn't help if one is expensive and the other is cheap, because yeah, we try to balance that. And this is what the lazy union by rank with path compression data structure achieves. It makes the fine set operation a little bit more expensive, but makes the union operation less expensive. How expensive in the amortized setting? This is exactly what we want to analyze. But first, let me explain to you the lazy union by rank heuristic with path compression. Lazy union by rank is a kind of generalization of this previous union by weight heuristic. union by weight would attach the smaller tree to the larger tree, small and large in terms of the number of nodes. Here, the union by rank heuristic attaches the tree with smaller rank to the tree with larger rank. Not the number, not the size, not the number of nodes, but the rank. Now you're supposed to ask, what is the rank? And this is actually a very subtle quantity because it's not really defined only in terms of the state of the data structure, but also about the history, how the data structure kind of evolved and developed over the sequence of operations from the user. So please bear with me for a moment. What the rank is, how the rank is defined precisely will be a pretty subtle point. But for now, as a first approximation, simply imagine that the rank is a depth. So now we attach the tree with smaller depth to the larger tree, not this tree with fewer number of nodes to the tree with larger number of nodes, but the tree with smaller depth. And one way of motivating this heuristic is if we attach the tree with smaller depth to the tree with larger depth, then the depth of the larger tree will be unaffected, because remember the depth is of a tree is the depth of the maximum node, and if we attach a tree with smaller depth to a tree with larger depth, then that doesn't increase the depth, except if both trees have the same depth again. So when ties need to be broken, then things start to become subtle and challenging. So idea is to realize now these disjoint sets as Forrest was under the depth, but we want the depth to be small. And so again, union operation now is realized with this union by rank heuristic is by comparing the rank of the trees, or more precisely, the rank of the nodes where x and y, and we take the smaller tree, the tree with smaller rank, and attach that to the tree with larger rank. So we attach x to y if x is smaller rank. Otherwise, we attach y to x if y has smaller rank. Well, if both have same rank, then we need to break ties arbitrarily, and here we do that. We merge one to the other, but then we need to increase our rank indicator, which is kind of motivated by the depth. But as we'll see, it is not equal to the depth. The depth is just a way of looking at things to provide you with some motivation of why this seems like a good idea. Okay, now let's try to visualize an execution. So the user wants to, so here you see the rank indicators attached. So the leaves have rank 0, height 0, imagine. The node has height 1, so this is kind of the toppled trees, right? So usually we think that the root has height 0 and lower nodes have larger height, but here it's the opposite. Same here, and here we have only one node. So if the user wants us to make the union of these two sets, this one has height, has rank 0, so it will get attached to the tree with larger height. This one has height 1. So this is what happens here. One pointer gets updated, and yeah, the point is, the important thing is that the rank of this tree does not increase because we have attached the tree with smaller height to the tree with larger height, which does not affect the height, which does not affect the rank. Now let's do the same again, visualizing the union of these two trees. Now what is the rank of this tree? Well, 0, 1, 0 here, and 2. So this tree has rank 2, has height 2, right? And this one has height 1. So when both get merged, union, then that means the tree with smaller height gets attached to the tree with larger height. in such a way that the height of the larger tree still remains 2, does not increase. That's exactly the point here. So yeah, this is all about height, not about size anymore as in the previous case. Now let's continue with this animation. Next time, maybe the user wants to form the union of these two sets, and now we need to break ties. Both have the same height, 1. So one of them needs to become the child of the other, and thus will increase the height. So let's see that here. Let's say pies are broken this way. Now this becomes a child of this tree, and now the height of this tree increases from 1 to 2. Okay, so this is the last case. If both have the same rank, then one gets attached to the other, which one doesn't really matter, frankly. But then the rank gets increased of the new dominant, the new root. Now we have here 2 trees, both of rank 2. And let's suppose these are to be merged. Then the same situation again. One needs to become the child of the other and will increase the height of the other. As you see here, now this one has height 3, right? Right. So this is a animation of this union algorithm, and we want to analyze that. Okay, so we have again our 3 operations. Now the make set operation still has constant cost. This time it's a union which has constant cost, right? But we now want to talk about the find set. Right, previously in our previous algorithm, union had logarithmic amortized cost. Find set has constant cost. Now it's the union operation which has constant cost because we need only to update one pointer. Let me show that again. Only one pointer gets updated, right? So union has constant cost, but now the find set operation is getting more costly because as the rank increases, that means also the running time for walking all the way up to find the handle, to find the root, right? So let's say the user wants us to find the unique handle of this. Well, let's start with this example. Let's say the user wants us to find the unique handle to this set, to this point. Then now we need in the find set operation to walk up all the way to the root. And the larger the height of the tree, the larger the rank, the more costly is that, right? So and now here the height has increased to 3. That means that the first case cost of the find set operation now becomes 3. So now we've arrived at the opposite kind of balance. Union is now a constant time, but find set can become larger and larger depending on the height. And this is where the other part of the name of the heuristic comes into account, namely path compression. So the idea behind path compression is that, well, if the user wants us to find the unique handle to, let's say, this node, then we do need to walk all the way up. There's no way of avoiding that, so we need to kind of pay and charge the user with or our bank account balance with this large cost corresponding to the height. But while walking all the way up, we can and should update the pointers to create a shortcut so that when the next time that the user wants us to find the unique handle to this element, we can jump directly to the root and did not need to follow all these edges again. So that's ideal, and that's perfectly corresponds to the amortized business paradigm. So if we need to pay a large price once, then at least lose that opportunity to make sure that it doesn't happen a second time, because repeatedly, that's really what matters in amortized analysis. And in this case, while walking all the way up, what we're going to do now is each time we walk up, and we visit this node, and we visit this node, and we visit this node. So it's already cost proportional to the height. But then we also update the pointer. This pointer, we redirect that not to go here, but to go directly to the root. And we update that pointer not to go here, but to go directly to the root, so that the next time when we need to find the unique handle to this element, we can directly follow the updated pointer, and thus, as the second time call to the find set operation will then have constant cost. So that's the idea behind path compression, installing all these shortcuts whenever the find set operation is expensive. And in pseudocode, it looks like this. This is a pseudocode for the find set operation. Find set of x returns the unique handle, the root. And if the parent of x is already absent, that means we are at the root, then we return that. Otherwise, we find unique handle to its parent recursively, so it's a recursive. How to find the unique handle of this? We find the unique handle of this element, which is the same, and we return that. But also we update the pointer here. So x parent pointer gets updated to point now to the unique handle of this root, so it gets redirected here. So here's the animation. So we update all these pointers during the recursive walking up. So it's a recursive way of walking up, not an iterative. And we update all these pointers to point directly to the root. And the next time the user wants us to find the unique handle find set of this element, then the cost is constant. Okay. So yeah, that's a intuition behind this heuristic. And now we want to state and analyze this heuristic. And we're going to see that, again, we have a sequence of n calls to make set and m calls to find set and union, that now the total time is m times alpha of n, where if you remember when we talked about alpha is the inverse Ackermann function. It's one of the slowest growing functions in computer science, right? So it grows slower than log n, it grows slower than log n, it grows more slowly than log n, and actually it grows even more slowly than log star m, which, as you recall, log star means how often can we iterate log before resulting in argument less than 1. So this is an increasingly slowly growing function, and now converting the statement of this theorem from total cost to amortized cost means we need to divide this total cost by m. That means the amortized cost is alpha of m, the inverse Ackermann function. So the lesson to learn from here is that this third algorithm, the Lazy-Unit by rank with path compression algorithm, has an extremely small amortized cost. For all practical purposes, the inverse Ackermann function is almost like constant. Remember, you calculated the log star and the inverse Ackermann function of the number of particles in the universe, and it was like, what, like 6 or 7? So this is a very, very small growing, and put differently, the Lazy-Unit by rank with path compression is an extremely efficient amortized realization of a data structure. So I see we're running out of time, so let me jump ahead and conclude chapter 4 with a brief summary. What we talked about, amortized analysis, we talked about motivation using the repeated binary counter, repeated incrementing, where worst case analysis of the number of bit flips gives a serious overestimate, whereas an amortized analysis, we saw that only 2-bit flips in the amortized setting. This is the same as we saw in the average case setting, but the framework is different. In the average setting, we start with the average counter value and increment once. In the amortized setting, we start with 0 and repeatedly increment. And then we generalize that to adding binary powers of 2 and saw that this still has constant amortized cost 2. But as soon as we also allow for decrement operation, then suddenly the amortized cost jumps and becomes as bad as the worst case cost. Then we talked about Fibonacci heaps, a kind of a generalization of binomial heap as a means of realizing a priority queue by Fibonacci heaps being a collection of relaxed binomial trees, whereas binomial heaps are a collection of strict binomial trees. Every order can occur at most once. We discussed how to implement the extract-min and decrease key operation in Fibonacci heap, and we analyzed the amortized cost using 2 bank accounts in our metaphor. And we saw that extract-min has logarithmic amortized cost, decrease key has constant amortized cost, and the analysis of the extract-min operation was built on our previous analysis of repeatedly adding binary powers of 2, because only during the extract-min operation kind of consolidation happens, whereas in a binomial heap, consolidation happens each time we call decrease key or merge operation. Then we talked about applications of this amortized analysis, namely in Prim's algorithm, which uses a priority queue repeatedly, and more precisely, it makes call to the decrease key operation more frequently than to the extract min operation, and therefore it's good that in our amortized analysis of Fibonacci heap, decrease key operation has constant amortized cost and extract min operation has logarithmic amortized cost, and this resulted in acceleration of the performance of Prim's algorithm when proceeding from binomial to Fibonacci heap. Binomial heap always has logarithmic worst case cost. Fibonacci heap has a decrease key operation has constant amortized cost. Then we recall Kruskal's algorithm, which builds on a data structure for disjoint sets, and we discussed the first implementation of disjoint sets as a forest of constant depth. Then we analyzed and we saw that this has bad amortized cost and bad worst case cost. Then we discussed the union by weight heuristic, and we saw that this is not just a heuristic, but actually results in an acceleration of the amortized performance of this data structure to logarithmic cost, because it is very rare for a union operation to be expensive repeatedly. And finally, we talked about a third algorithm, namely the lazy union by rank heuristic with path compression, where now we don't attach the smaller tree to the larger tree, but we attach the tree with smaller rank to the tree with larger rank. And it's one way of getting intuition about the rank is to think of it as the height, but that's not entirely accurate, because we also have this path compression, which kind of accelerates the find set operation when called repeatedly. When called first time, it may be expensive, but during that expensive execution, we kind of install and update the pointers to become shortcuts, so that the next time it becomes cheaper, and therefore repeated calls to find set are actually very cheap. And how cheap? This is described by the inverse Ackermann function, one of the functions we discussed here in the chapter on fast and slowly growing functions. I didn't prove that here. What we did prove is the running amortized cost, which is log star, and then we ran out of time. So that's all about chapter 4, and as I see, right. So we have kind of like 10 minutes left. So let me pause here and give you a kind of a preview of our next chapter 5 here. So I've stopped the sharing. Right. So in chapter 5, we want to talk about randomized algorithms, and of course, we want to analyze randomized algorithms. So how we start with the motivation, motivation being reliability. So engineers have put in so much effort to make our computers reliable, and reliable means deterministic, so that when we perform the same calculation the second time, the result should of course be the same. And it's so obvious to us nowadays that we kind of take it for granted, but this was a huge effort. And now we're kind of avoiding that effort by introducing randomness, and thus possibly wrong results, or maybe different executions at least give rise to different behavior, maybe different running times, or maybe even different results. Why would we even do that? And we're going to see that reliability is almost as good as full determinism. Then we discuss how to obtain randomness, because as engineers have made our computers so deterministic, it's actually suddenly very difficult to obtain true random, for example, bit flips. Random bits has become surprisingly challenging. We discussed two types of randomized algorithm among many more types, namely Las Vegas algorithm versus Monte Carlo algorithms. We give a first but important application, I mean, primality testing, testing whether a given integer is a prime number or not. There exist efficient deterministic algorithms, but in practice, it's much easier and much more faster to do that in a randomized way. We see how we can decrease the probability for such randomized algorithms to give wrong errors by means of amplification. First, one-sided algorithms with one-sided errors, and then algorithms with two-sided errors. Another application is polynomial testing, testing with a black box polynomial, multivariate polynomial is identically zero or not, using randomized evaluation and analyzing that. And the analysis hinges crucially on a famous lemma. It's called Schwarz-Siebel lemma, but it's had been found before. And we discussed then an application of that black box polynomial test analyzed using Schwarz-Siebel in testing whether a graph admits a perfect matching or not. And we conclude with perfect matchings using the tacit determinant, symbolic determinant approach of black box polynomial testing. So that's all perspective for next time, Thursday. For now, time is up, but as usual, I will stay online and be available to answer your questions.